What's up, guys and girls? Raj here, back from Washington DC AWS Summit. So this week was very exciting for me. I presented 3 talks there. The first talk was container and serverless monitoring and observability. So that was recorded. The second talk was container and serverless security. So this talk was also recorded as well as broadcast to thousands of people online from the official AWS page. And the third talk was a whiteboarding talk. It was on serverless and container better together. This talk went over how to choose whether serverless or container, what are the different design factors, etc. So the first 2 talks, since they were recorded, they will be out in official AWS channel in like a couple weeks. But the third talk, the chalk talk or the whiteboarding, serverless and container better together, was not recorded because it was very interactive and like a whiteboarding session. So a lot of you reached out to me, said, hey, can you go over what you actually presented, because not everyone could get in the session. So in today's video, I'm going to go over the exact same content that I created and went over in the DC Summit, including the whiteboarding part. All right, let's get started. So when it comes to considering serverless or container, these are some of the decision factors: scaling, resource configuration, high availability, AWS service integration, security, and management. So all right, so let's go through how does Lambda and containers scale differently. So I'm going to jump into the whiteboard for this part. All right, so let's start with Lambda first. So you create your Lambda function, and when there is no traffic, there is no invocation of the Lambda. So as soon as a traffic comes, the underlying Firecracker VM comes up and then loads your Lambda code and executes the Lambda code. Now what if traffic increases? So the important thing to remember is each traffic request will provision another instance of your Lambda, right? So as the traffic increases at the same time, more copies of your Lambda will get provisioned and start running. So the scaling configuration is super straightforward. Because every traffic connection is just creating a new Lambda instance, there is really no scaling configuration required. Because if there are 1,000 traffic coming, it will spin up 1,000 of your Lambda instances. Now one disadvantage could be, since each new traffic is provisioning a new Lambda instance, you could experience cold start. So there are caveats to this. So for example, let's say all this Lambda is running, and then after a few seconds, the code stopped executing, so you got your return back. Even when the execution is done, the underlying Lambda virtual machine will stay warm for a certain amount of time. So within that time, if new traffic comes in, they will reuse those warmed up containers. So it's not like every time traffic comes, a new Lambda instance will get provisioned. So now let's take a look at how does container scale. So let's consider Kubernetes first. And with Kubernetes or AWS Kubernetes services, Elastic Kubernetes service, we will assume that the workers are running in EC2. So within EC2, your containers will run within a pod. So pod is the minimum deployment unit in Kubernetes. Now what will happen is this pod will keep on running. So let's say this is like a web server or like an API. With Lambda, when there is no traffic, there is no Lambda running. So you don't pay for that part. With pod, the pod will keep running even if there is no container. And when the traffic comes, the big difference between this pod and Lambda is one pod can accept multiple traffic connections. And when the traffic comes and your container is running inside the pod has its own CPU and memory. Let's say for simplicity, we are just showing CPU. So there is one traffic, The pod is handling that, so the CPU went up a little bit. And then more concurrent traffic comes in, right? So let's say 4 traffic comes in, everything being served by the pod at the same time. It's not one after another, right? Because this pod can handle all this concurrent traffic, and at that point the CPU, let's say, went up to 95%. So now with Kubernetes, you have this concept called metrics server and horizontal pod autoscaler. So with metrics server, you can track the CPU memory of the pod. And then on top of the metrics server, using the metrics, you can configure HPA or horizontal pod autoscaler. And using this HPA, you could say if the CPU utilization of this pod, let's say, is 90% or 95%, spin another pod. So Kubernetes will try to schedule another pod within the same EC2. So let's say we have capacity in the EC2. So another pod spins up, and that pod start accepting new traffic. But beyond the pod, CPU, and memory, this EC2 also has CPU and memory. So for this diagram, I'm just showing 2 pods, but in reality, depending on the EC2 type, it will probably have more pods. After a certain point, the EC2 CPU will also reach a threshold. And then, using cluster autoscaler or the newly released Carpenter, when the Kubernetes will try to schedule a new pod, it will see that this EC2 has no more capacity left. So at that point, cluster autoscaler or Carpenter will kick in and create another EC2. And then the next pod will be scheduled in that new EC2. And it will start accepting traffic. Now when it comes to cold start, so since this pod is running, for all the traffic getting served by this pod, there will really be no cold start because this is already up and running. Now when another pod needs to be provisioned within the same EC2, actually what Kubernetes does is when this first pod was spun up, it will cache the container image that's running within it. So it will grab the container image from some sort of registry, it will spin up the pod, and it will also cache this container within this EC2. So when the other pod's coming in, it will be relatively faster. And when a new EC2 gets spun up, the first time it will take a little bit longer. But again, how long it takes, it depends on your actual image size and other configuration. So now what if with Lambda, you cannot tolerate any cold start? What if it's a critical workload? So in that case, what you want to do is use provisioned concurrency for Lambda. So with provisioned concurrency, it will actually start acting like the pods, right? Even though there was no traffic, the pod was still up and running. So with provisioned concurrency, you can say that I need 10 instances of my Lambda up and running, even if there is no traffic. So let's say I'm just showing 4 instances of your Lambda. They will up and running, there is no traffic, and when traffic comes up, let's say very fast, they will just go to the already pre-warmed Lambda, so you'll have no cold start. 2 things to keep in mind, that provisioned concurrency is not free, so you do have to pay for it. But secondly, you can control provisioned concurrency. So if you know when a big traffic is going to hit your application, you can schedule this provisioned concurrency based on date, time, etc. You can also auto scale this provisioned concurrency. Another thing to keep in mind is if the same Lambda is scaling out, all the scaled out Lambdas will actually use one IP address. So before, couple years back, Each of these scaled up Lambda used to take separate IP address and you would run out of IP address, but not anymore. Now all the Lambdas in the same subnet and using the same security group will reuse the same IP address. But with Kubernetes, same for ECS as well, each pod will actually consume different IP address. So this will be IP address 1, this will be IP address 2, this will be IP address 3. So as your application scales up a lot, you have to make sure that the VPC where your Kubernetes cluster is running has sufficient number of IP addresses. So at a certain point, you might come close to exhausting the number of IP addresses. So there are a couple of techniques to avoid this. One is you can add a secondary CIDR range to the EKS VPC, or you can use IPv6, which gives you way more IP addresses, etc. But you do need to be cognizant of IP address exhaustion with Kubernetes scaling. And the same concepts apply for ECS as well. So instead of pod, it will be like a task which is running your container. But the IP address part stays the same. The scaling out part also remains relatively same, but instead of HPA cluster autoscaler, you will use AWS autoscaling because ECS is a native AWS service. So alright, so now we understood how Lambda and Kubernetes on EC2 mode scales differently. So let's take a look at Fargate scaling. So I'm just going to delete the Lambda part. So with Fargate, everything actually stays the same. Only thing you don't need to worry about is the EC2. So when you schedule a container or when you deploy a container, you have this deployment file or the pod specifications file where you mention what is the container image, what is the HPA scaling criteria, where should the image come from. That's all you need for Fargate. You do not need to run any EC2 worker node. You just give your pod specification file to AWS, and AWS pins up some underlying Firecracker VM and it runs your pod. So to you, only thing visible is the pod. You do not see or need to maintain the underlying EC2. So, but the same concept, as more traffic comes in, this pod which is running in Fargate, the CPU utilization goes up, and after a certain point, another Fargate instance comes up, runs your pod. All right, so now we understood how Lambda, EKS on EC2, ECS scale, and Fargate scale. So another thing I want to talk about is App Runner. So this is the newest service. So App Runner is quite straightforward. With App Runner can only scale based on number of incoming connections. So when you schedule App Runner, you specify some sort of capacity units, like App Runner capacity units or ACU. When you provision an App Runner, it will actually provision an ALB for you. You don't need to do it separately, it will do it for you. So let's say I'm gonna say App Runner, and as more traffic comes in, it will scale out more App Runner VM underneath, and this will run your container. So with Kubernetes or even ECS, you can scale based on CPU, based on memory, or even other CloudWatch metrics. So you can use tools like KEDA with Kubernetes to scale your Kubernetes pod beyond CPU memory. You can do it based on concurrent connections, based on cache usage, whatever you want. App Runner definitely restricted on that. All right, so we understood the different scaling. So one of the big factor is Lambda scaling, ECS scaling, App Runner scaling. They all use AWS components, but Kubernetes scaling requires understanding open source components, right? We saw you need to understand and install metric server, you need to understand HPA, cluster autoscaler, carpenter, etc. All right, so now let's take a look at Lambda resource configuration. So Lambda, you allocate memory and CPU gets allocated proportionally. You can choose Lambda memory from 128 megabyte to 10 gigabyte in 1 megabyte increments. The CPU core is allocated proportionally between 1 to 6 cores. Maximum runtime of Lambda is 15 minutes, and you cannot choose underlying infrastructure. So if you have a GPU workload or some specific CPU intensive machine learning workload, you cannot say, hey, run this Lambda in a GPU infrastructure or CPU heavy infrastructure. All you can select is memory, and then CPU will get allocated proportionally. Now container is very powerful here. In container, you can configure CPU and memory allocation. So each pod, you could say how much CPU it should take, how much memory it should take. You have option to do not assign anything at all, but it is not recommended. So if your pod has some bad logic, it will take all the CPU and memory of the EC2 instance and keep scaling everything, and you will get charged a lot. So we always specify request and limits for your pods. You can choose underlying EC2 instance type appropriate to workload. So if you have a GPU workload running, you can choose GPU instances, etc. For Fargate, you have the maximum memory of 30 gigabyte and maximum CPU is 4 vCPU. So there is some limitation there. For App Runner, maximum memory is 4 gigabyte, maximum CPU is 2 vCPU. All right, so now let's take a look at high availability. So high availability means that your application should run in more than one availability zone. So even if one availability zone goes down, your application should be up and running. So Lambda has an advantage here. Inherently, without you doing anything, Lambda runs in multiple availability zone under the hood, the same Lambda, and you do not need to pay extra for this. And internally, the Lambda service will work as a load balancer. So when the traffic is coming, it will automatically route the request. Even if one availability zone goes down, your application will still be up and running. Now for container, you have to ensure high availability. So if you are running EC2 and your pods are running within EC2, so EC2 will run in one availability zone. To make it highly available, you need to spin up another EC2 in another availability zone, and you need to run the same container in a pod within that EC2. Don't confuse high availability with replica. With replica, if your pod is running in one EC2 and your pod goes down, it will spin up another pod, but there will be a time delay. High availability means even if one availability zone goes down, your application should not face any disruption. How would you achieve that? For EKS with Kubernetes, pod topology spread can be used to distribute pods in multiple AZ. For ECS, task placement strategies can distribute tasks in multi-AZ. Now let's take a look at service integration. So this is the superpower of Lambda. Lambda out of the box integrates with over 100 plus AWS services. So for example, if someone puts a file on S3 bucket and you want to process that file, someone puts messages on SQS, SNS, you can trigger Lambda out of the box with just click of a button or just one API. And it has superior integration with API gateway. So if you want to make a microservice, and we'll see this as well in a design, very easy to integrate with Lambda. Now container is not as powerful here. With Kubernetes EKS, you need to use Ingress, an AWS load balancer controller, and you can expose your pod to an application load balancer or network load balancer. But let's say you want to trigger your EKS job or EKS pod once a file is put into S3, or trigger some application running in container when a message is pushed to SNS. You cannot really do that out of the box. So you have to create the orchestration layer, So for the S3 example, you can trigger a Lambda from S3, and that Lambda can call this ingress and trigger your pods. ECS, so the task is for ECS, has a little bit more flexibility. Since it's a native AWS service, it integrates directly with API gateway. So EKS, you cannot expose those pods with API gateway. It has to be a load balancer. But with ECS, you can expose using API gateway and Cloud Map. A typical API gateway pattern, if you want to use API gateway with Kubernetes, is API gateway to load balancer to task or pod. So I've given both ECS and EKS here because sometimes you would want to use API gateway instead of load balancer to front your task or pod, because API gateway gives a lot of features which is not present in ALB, such as payload validation, payload transformation, very easy authentication authorization. Even though both can do authentication authorization with OAuth and all that stuff, but API gateway, you can authenticate using API key, you can assign quota, etc. I have a separate full video on choosing API gateway and load balancer. I'll give the link up top. Feel free to go and check it out. All right, so now let's whiteboard the use cases for both Lambda and container for microservices as well as event-driven architecture. All right, so let's start with a microservices pattern. So Lambda is pretty straightforward. So you can use API gateway or a application load balancer, and they could just call the Lambda. So with API gateway, you have direct integration. With application load balancer, same direct integration. You can use Lambda as one of the target groups, and you can send the traffic there. Now, one thing to keep in mind, network load balancer does not have a direct integration with Lambda. So if you are using network load balancer, the network load balancer will send the traffic to application load balancer, and the application load balancer will send the traffic to Lambda. How about logging and monitoring, observability, all that stuff? So Lambda, out of the box, will integrate with Amazon CloudWatch. I'll just write CW as in CloudWatch. You do not need to do any additional configuration. So Lambda will start writing the logs to CloudWatch, will start putting monitoring metrics in CloudWatch, and if you want additional tracing, you can integrate X-ray. Again, that's just click up a button for the main X-ray, and then you can instrument your code easily as well. Now let's take a look at the same thing with containers. So with containers, so let's say we start with the VPC, and I'll go with the popular one, Kubernetes or EKS. See, I'm wearing a EKS shirt. Thank you to one of my coworkers who gave me this amazing shirt. I love it. Okay, so VPC, and then you have private subnet. So let's say you have two EC2s running in the private subnet. EC2, EC2. How does the flow look like? So you'll have a container image saved in a container repository. So let's say this is ECR. So let's do a different color marker. Okay, let's spice things up. Okay, so let's say you have your container image sitting on that ECR, and then you have to deploy this using some deployment manifest with some CI/CD pipeline. So what will happen? You folks know this already at this point. So a pod will spin up, and this pod will have a container inside running in it. Similarly, you could have another application, another container sitting on ECR, and then you deploy that, another pod will spin up, it will run here. I mean, even though I'm showing two different EC2s, that doesn't mean that they will run on separate EC2s. I just drew them a little small. Highly possible if the EC2 has a lot of capacity, the same EC2 can run 2 pods with different containers each. So they are running in private subnet. So to go into those pods, you need a load balancer. So this, let's say for simplicity, I put application load balancer, and this we'll call ingress. And this load balancer will accept traffic, and then it can route traffic to different pods based on the URL. Now, this ingress is an open source component. Even though AWS gives you ALB ingress controller, you need to install it and maintain it. So this is just the microservice, right? And if you want, you can also put API gateway on top if you like API gateway features. So this is optional, so I'll put optional. You can also run API gateway inside the Kubernetes cluster using some tools like Nginx, Kong, etc. But I'm not going that route. I want to keep the conversation using AWS services. How about logging, monitoring, and observability? So nothing is provided out of the box. Since Kubernetes is open source, you have to install the components. So for monitoring, there is a very popular agent called Prometheus. So let's take another color. I'm going to take a red color, monitoring. It's like monitoring critical stuff. So I'll just put an asterisk. So monitoring, let's say Prometheus will run as a daemon set. So that means on every node of the cluster, it will run another pod. So even though I'm just putting an asterisk, think of this as a pod, one pod running on each node. And they will collect all the metrics and send it over to Prometheus. Okay? And then you need to use Grafana on top of those data to create the metrics. So how about logs? Similarly, for logs, one of the most popular agent is FluentBit. Similarly, FluentBit will also run as a daemon set, and they will send everything to a log aggregator. You could use CloudWatch if you want, or it could be Splunk, etc. So I'll just put CloudWatch / Splunk. Similarly, if you want tracing, you could use X-ray if you want. So X-ray again will be a daemon set. So I'll put this here, and this will send to X-ray. Again, X-ray is AWS tracing service. If you want, you can use your open source component like Jaeger, totally up to you. All right, so crux of the matter is, when you need to create microservice, Lambda is pretty straightforward. Kubernetes is cool, but it requires a lot of overhead. So you need to install all this stuff, you need to maintain it. So AWS is making it easier. So AWS recently released ADOT, or AWS Distributed Open Telemetry, which gives you the agent, so you don't need to go install all this separately. It gives the agent currently for monitoring and tracing. The logging agent is in the works. So you can just install ADOT, you can configure, you can send the metrics to Prometheus or CloudWatch. Similarly, for tracing, you can send it to X-ray, Jaeger, etc. All right, so this is how the microservice flow looks like. Similarly, the Fargate will be very similar with EKS, even you are not doing the EC2. So now with Fargate, you don't have daemon set, right? Because Fargate, you don't have the visibility to the EC2. You only have a sidecar. So not everything will be applied. So you have to check that. For example, if you are doing network policy, Fargate cannot support network policy because Calico you cannot run. Even for the logging, depending on the log aggregator you are using, you need to check whatever open source tool you are using, whether they could be run in a sidecar or not. All right, so that was microservice. Now let's take a look at event-driven architecture. So this is where Lambda really shines. When we talk about event-driven architecture, we mean that it is processing asynchronously using some events. So first, quickly go over what is a synchronous architecture and what is asynchronous architecture. So synchronous architecture is you get the response in the same invocation. So one example could be you have API hosted in API gateway, it's calling a Lambda, getting something from database, and then returning it to the user, right? Now let's say the traffic increases, so more users come in at the same time. The API gateway API needs to scale, the Lambda needs to scale, and the database needs to handle that much concurrent connections. And all these components need to scale together at the same time. So what if you reach a certain point when your database can no longer accept any more concurrent connections? So if this database call fails, the whole chain will fail. And to reprocess it, the user needs to invoke the API again and go through the whole chain. Now, event-driven architecture, if I redo the same thing, let's say you still have the API gateway. Instead of calling the backend compute, it can put the message inside a SQS. So the messages are getting into SQS, and then a Lambda can grab the messages, process based on the rate that the database can handle, and then insert into the database. So you obviously have to balance this. Not everything could be event driven. So this is just the difference between synchronous and asynchronous architecture. So now let's take a look at other event driven architectures. So some of the very popular event driven architectures are, let's say you have files coming in S3. You want to get processed every time a file comes in. You can invoke the Lambda, it does something, put something into database. Another example could be you publish a message to a SNS topic and you want to notify multiple people. From here, you can directly send it to cell phones, or if you want, it needs to be processed, you can invoke Lambdas for each of these. Similarly for EventBridge as well. If you want to do the same thing with container, there is really no easy way. So with S3, there is no way to trigger. So this Lambda needs to trigger the ALB that is fronting the pod which is running the container, right? So it's a little bit of hassle, a little bit of orchestration. The newest event-driven service is Amazon EventBridge. So there's a lot of features added. So with EventBridge, you can selectively fire different targets for different messages. So you can put all the rules inside EventBridge. So again, you can have two Lambdas. For this message, you can fire Lambda 1. For the other message, you can fire Lambda 2. Now, you can also fire ECS Fargate from EventBridge, which is nice. But if you want to fire EKS Fargate, again, there is no direct integration. You have to call this Lambda ALB, or EventBridge can call API URL. So if your application load balancer that is in front of the pod has a URL, you can call that URL of the LB. All right, so these are some of the big examples of event-driven architectures with Lambda. All right, so now let's discuss the security. So security is a huge topic by itself, and I gave a separate 45 minutes talk just on security. That talk was recorded. I will share the link once AWS makes it public in AWS's YouTube channel. Just the big picture. If you are running containers on EC2 worker node, you need to manage those EC2 worker nodes. So if you want to create your own AMI and do all that, that's fine. But remember that first time it's easy. You just have AMI, you install it, okay, everything is great. But there will be security vulnerabilities, and then you need to immediately patch it and rehydrate it. You need to take care of all that. You can use AWS provided AMIs. So AWS provides you AMIs. Currently, we provide AMIs for Amazon Linux 2 and BottleRocket. So you can go use those AMIs. But again, even though we give you AMIs, you have to orchestrate it. Like you have to call the API to do the rolling upgrade. And if the AMI does not fulfill your security compliance, you need to create those. With Fargate, there is no EC2, so you don't need to patch or care about the underlying infrastructure. AWS will take care of that infrastructure. Similarly, for Lambda, it's AWS's responsibility to keep it safe. You need to define what does security mean to your organization. For example, if you require FedRAMP high compliance, in that case, Lambda is FedRAMP high compliant, EKS on EC2 is FedRAMP high compliant, EKS on Fargate is not FedRAMP high compliant, ECS both for worker node and Fargate is FedRAMP high compliant, App Runner is not FedRAMP high compliant. So in that case, you have the compliance from AWS, AWS gives you the artifacts, and that's good. If your security requirement is all the traffic should be private. So when the traffic hits the application load balancer or API gateway, and then on the back end, either Kubernetes, Lambda, whatever you use, the organization's requirement is it needs to be within the VPC or private AWS backbone and not public internet. So you can achieve that for using Lambda, containers on EC2, Fargate, all of those, right? So it doesn't matter. All right, so now that we understood those main factors, let's go over a management part and then summarize what we learned so far. So management is also an important factor. At this point, you understand what tasks your team needs to do when you want to manage infrastructure like EC2s. How important is open source to your team? Kubernetes is cool, but consider the learning curve and also think about day two operation. So just doing a proof of concept or deploying the project for the first time is nice, but things will break down the line. So make sure you have a day two operation plan, whether your developers will support the application or you need to train other people, etc. So at the end of the day, there is no prescriptive guidance. So I just went over all these factors: scaling, resource configuration, high availability, integration with other AWS services, security in very high level, management. You need to consider all these factors and then choose based on your organization. That was the actual chalk talk I gave in DC Summit. Thanks to all of you who actually came to my sessions. I know you have a lot of options. There are a lot of talented presenters in DC Summit. And thanks for choosing my session. Spend your valuable time with me. Also, thanks to everyone who said very nice things to me. A lot of you stopped me and said that, hey, my videos or teaching helped you on your cloud journey. It really makes me very humble. And I'm very, very glad that you selected my content to learn. I know you have a lot of options there as well. All right, so I'm back from DC. I was exhausted, but I was happy exhausted. I was super pumped. So back to normal schedule. If you like this video, as always, click the subscribe button, click the like button, ask me any question in the comment section. And that's it for this one. I'll see you guys and girls in the next video. Bye.